Today we are going to talk about mass spectrometers and how those are built and how they use an electric field and a magnetic field to manipulate charged particles. Okay, so there's a couple of crucial components. There's like three main components to a mass spec. Okay, and in order to prepare your sample, the first thing that you have to do is ionize the sample so that you can get a charged particle. So, and just so you know, a mass spectrometer, if you didn't learn about it, I think I might have talked about it in chemistry when you were with me, but I don't remember. What it does is you inject a sample, some chemical into it that you don't know what it is, and then based off of the atomic masses of the different ions that fragment off of the sample, the machine can tell what the sample is, and it gives you little peaks that you read out, and you learn how to read those peaks and piece back together what the complete molecule is. So that's kind of the idea of this in a nutshell. So the first thing you have to do, though, is ionize the sample so you can have charges. That way the electric field and the magnetic field can interact with it. And then you have to send that charged particle through the mass spectrometer. So the first step of a mass spectrometer is going to be the accelerator. Okay. And in that previous section of notes, when we were talking about the CRT, we called it the Electron Gun. That's the same thing as the accelerator here. Except it's not always electrons. It could be protons or other positively charged or negatively charged ions. Okay, so we're going to say, all right, we've got this positive charge. It's connected to a voltage source. We have these parallel plates, just like in the CRT. And there's a slit in between those parallel plates, which means that an electric field is forming between the parallel plates. Okay, so we could say that this parallel plate is the positive plate, and this is the negative plate, and that means that the electric field lines are going to be going from left to right. Okay, and since they're going from left to right, a positive charge would move in the same direction as the electric field lines. Okay, so the kind of main idea of the accelerator section of mass spectrometer has to do with energy. Okay, so we're going to use a voltage source to accelerate some charged particle, which we're going to call Q, and we know that we have conservation of energy. So the kinetic energy gained by this charged particle is going to be equal to the electric potential energy lost overall by the voltage source. So then we're going to use the idea or the equation for kinetic energy, 1/2 mv squared. We're going to say that change in kinetic energy, and this v that we're talking about, that's going to be the tangential velocity squared. Remember, we said that if you send a particle into a magnetic field and you try and accelerate it, then you're going to get a magnetic force that's going to try and start making it curve into circular motion. So the velocity down here, we're going to say that's the tangential velocity. And then electric potential energy's equation is still QV, where this V is voltage. Notice the vector symbol over this V and not over this one. So this is the scalar voltage, and that's the vector velocity. Okay, so then the next piece of the mass spectrometer is this middle section, and this is going to be the velocity selector. And we're going to decide how fast we want this charge to be moving. And we're going to do that by playing with the magnetic field, which is symbolized by capital B, and the electric field symbolized with a capital E. So we've got a uniform magnetic field symbolized by these X's. And remember that those X's indicate that we're going into the page. Okay, so the magnetic field lines are pointing into the plane right now. And this charge here, this positive Q charge, is passing through the magnetic field. So the magnetic field's pointing down and the charge is trying to pass through all these field lines. Okay? All right, so we have this region of uniform magnetic field, and only charges that have a specific velocity will be able to go through that magnetic field, okay, undeflected, all right? Because remember, just a moment ago, I told you that if we start trying to pass a charge to this magnetic field, there will be a magnetic force which starts trying to make it go through circular motion, okay? But there is one precise exact velocity that will allow the charge to pass through the field undeflected, and that's what we want to try and figure out right now, okay? So we can say that if we want that charge to go through this magnetic field, that means that we need to balance the forces that are acting on that charge. Okay, so if there's going to be a magnetic force acting on it to try and curve it in one direction, then we want to have a different force that is equal and opposite and pushes it back exactly the same amount in the opposite direction. And then that would cancel out both forces. And since we are talking about moving it through a magnetic field and an electric field, then the two forces that we would have would be a magnetic force and an electric force. So those are the two forces that we want to set equal to each other. Okay, so we want the magnetic force and the electric force to be equal and opposite to each other. So that's what we've got set up here in this equation. The equation for magnetic force is Q, the charge, V, the tangential velocity, B, the magnetic field strength, and then sine theta, because we want it to be a dot product instead of a cross product. Okay, so we have QVB sine theta for the magnetic force, and then we've got QE for electric force. So the angle between these two, remember when we're talking about this sine theta here, theta is the angle between the two vectors in the equation. So V, the tangential velocity, that's one vector variable, and then B, the magnetic field, that's the other vector variable, okay? So remember we said that the magnetic field lines are pointing down, okay? And this charge Q right here, it's got a velocity vector that's pointing in this direction. So the angle between down and to the left is 90 degrees. So that's why we're saying that this theta here is equal to 90 degrees. And the sine of 90 is 1, so that means this term, sine theta, is just multiplying by 1, and we can ignore it. Okay, so now we're trying to figure out, because this is the velocity selector section of the mass spectrometer, we're trying to figure out exactly what velocity should this charge be moving at so that it can pass through the magnetic field undeflected. So we're going to rearrange the equation to solve for the tangential velocity here, okay? So we've got Q on both sides of the equal sign, so those can just cancel out because the charge stays the same the whole time. And then that gives us VB equals E, and then we can divide by B on both sides. So the exact velocity that that particle needs to move at should be E over B, the electric field strength divided by the magnetic field strength. Now we need to figure out what direction these things are moving in. So the straight finger right hand rule tells us the direction of the magnetic force. Okay, so see if I can do this under the camera. We're going to point our palm of our right hand in the direction of the magnetic field lines, and they're pointing down into the page. So I'm going to put my hand like this. Then we want to point our straight fingers in the direction of the velocity vector. So I'm going to turn my fingers in this direction, okay? And then my thumb is going to be pointing in the direction of the magnetic force that's going to be pushing on the charge. So that means that the magnetic force is going to be pushing up on this positive charge. trying to make it curve like this, okay? Now let's talk about the electric field. If we, or the, excuse me, the electric force. If we want the forces to be equal and opposite, then that means we need the electric force direction to be down to counteract the magnetic force going up. So now, if that's the case, if we want the electric force to be pointing down, we need to figure out which way the electric field lines are going to be pointing, okay? So, because this is a positive charge particle, we know that the electric field lines are going to point in the same direction as the electric force, okay? So that means that the electric field direction must also be downward, okay? We can just draw that out here real quick. If these are the parallel plates that have charge, and I put positive charge up here on top, and I put negative charge down here on the bottom, then that means that I put a test charge in the center, or in that electric field, and that test charge is a small positive charge, and it defines the electric field. That means the electric field lines would be moving in this direction, okay? And that means that this charge would experience an electric force that's going to push it in this direction. So the electric force acts on a positive charge in the same direction as the electric field lines. So that's how we know that the electric field lines are going to be pointing down this direction. So then we are going to get to the third section of the mass spectrometer, and that's where we're going to remove the electric field, okay? And we're only going to have a magnetic field at this point, okay? So there's going to be a tiny little slit right here, and only particles that are able to pass through undeflected will make it through this slit, okay? Particles that don't have the velocity equal to E over B, they're going to get deflected and they're going to strike up here somewhere, okay? But particles that have the exact velocity we're looking for, they're going to make it through that little opening, and then they're going to get to pass through this little opening here into this section where we just have a magnetic field and we don't have an electric field anymore, okay? Now, once we remove the electric field, we no longer have this equal and opposite force taking place. Now, the only force that we have is the magnetic force. So, as soon as the particles enter into this section, they're going to immediately go into circular motion. So, we still have a uniform magnetic field, so it would be some precise number of Tesla, you know, and it's moving in some specific direction. We have no electric force. The particle's going to go into circular motion, and this would be the path that would be taken, okay? So we have some tangential velocity that moves in, okay? And it's moving to the left to start with, all right? And the magnetic field lines are still pointing down. So if I do the same hand motion, then that means that the magnetic force is still pushing upward on the particle, okay? So the particle is going to start to curve in this direction. But notice what happens as I start moving the particle, that tangential velocity vector here, it would be changing the whole time, right? So as it makes its way around the circle, the tangential velocity would be moving around the circle tangent the whole time. So that means each of these green arrows, those are velocity vectors. Our fingers are supposed to point in the direction of the velocity vector. So when it first enters into the magnetic field, the force is pointing up. Then as it starts being pushed on by that force, the tangential velocity vector changes, which means the force vector over here changes and it starts moving inward. Okay, so we can see that as this particle makes its way around the circle, my thumb represents the force vector, and that force vector is always pointing inward towards the center of this circular path. After this particle has made it exactly halfway around the circle, it's up here at this point where it's going to run into a screen. And this screen is it's either got a phosphorescence to it or it's got a detector on it so it knows when it's been struck by a charged particle. And since we have either a fluorescent quality to the screen or a detector worked into the screen, we can measure the radius of the circle. Okay, so we know that from here, from this entry point up to where the particle strikes, that's the diameter. Okay, that's half of the circle, and so we can divide that by 2 to figure out what the radius is. Imagine that this particle enters the screen and it comes up here and it strikes the screen at this location. Okay, that's half of a circle. So if we had the other half of the circle like this, that means that this length from where it enters into the magnetic field to where it hits the screen, that's the diameter of the circular path that it took. So of course half of that would give us the radius of that circular path. Okay, so let's look at the circular motion calculation part of this. Okay, so we can say, all right, the centripetal force is the net force in the n-axis. That's equal to mass times centripetal acceleration. The centripetal force is also equal to the magnetic force. We can set those two pieces equal to each other, expand the equations like sine theta is still going to be 1 because theta is 90 degrees. Then we have a tangential velocity term on the left, and we have tangential velocity squared on the right. So we can cancel one of them out on each side. That gives us Q times B equals mass times tangential velocity divided by radius on the right-hand side. And then the mass spectrometer will often put things in terms of charge to mass ratio. So we're going to divide by the mass on both sides. So you get a charge to mass ratio is equal to tangential velocity divided by magnetic field times radius. Okay. So the speed is known from the velocity selector section. So if we look back here, remember we had a particular velocity that was able to pass through the velocity selector section, and it entered the magnetic field over here at that specific velocity. And that velocity was E over B. So that could be plugged in right here for this tangential velocity. We could plug in E over B if we needed to, if we had some, exact values, or we wanted to simplify this further, okay? The radius could be measured, and the magnetic field strength is also known because we're in control of the machine. So that could help us to figure out what the charge to mass ratio is, or if we knew what the charge was, we could figure out what the mass of the particle is, which is why this is called a mass spectrometer, because it will figure out what the mass of the particles are. All right, I'll read it, of course, as we go through it. So it says, after a beam of protons is accelerated by 1,000 volts, it enters a region with a uniform magnetic field of 0.50 Tesla. Find A, What magnitude and direction of electric field is needed to make this proton beam go straight, undeflected through this region of uniform magnetic field? And B, the electric field is then turned off so that the beam of protons enters into circular motion and the region of uniform magnetic field. Find the radius of the proton's circular motion. Mass of a proton is 1.67 times 10 to the negative 27 kilograms. Okay, so those are our two parts of this question so far. So right there we have 1/2 times the mass times the tangential velocity squared is equal to QV. And so we can solve this equation for the tangential velocity. Say that 1/2 mass times the tangential velocity squared equals Q times V, the voltage. So multiply this side by 2, divide by the mass, and take the square root. So the tangential velocity then is equal to the square root of Q times the voltage times 2 divided by the mass. Okay, so when I plug in my information, you can just solve this side and then do this product over here, divide, take the square root, or just plug into the equation we got, however you want to do it. But this is what you should get, 4.377 times 10 to the 5th meters per second. Okay, so now let's look here at this little diagram that I have on the top that goes with part B of this question, okay? So we said we've got our proton and it's moving undeflected with some velocity through a uniform magnetic field, okay? And this says, like letter A says, what magnitude and direction of electric field is needed to make this proton beam go straight and undeflected, okay? And then letter B was the electric field's turned off, find the radius, okay? Well, we just figured out the velocity that the proton's going to have when it goes through that magnetic field. But now we need to figure out which direction the electric field is going to point in order to have the electric force be equal and opposite to the magnetic force. So if we've got these dots here, the magnetic field is being represented by dots. That means that we're going to point our palm straight up because those dots means that it's coming out of the page, okay? And then, get up to this one. So my palm's still pointing up, and now my straight fingers are pointing in the direction of the velocity vector, which means that my thumb is pointing in the direction of the magnetic force. So in this case, it will be pointing down. That means that we want the electric force to be pointing up so that they're equal and opposite to each other. So if the electric force is pointing up on a positively charged particle, then that means the electric field lines are going to be pointing up as well. So then let's look at the rest of this question. So the way that I'm solving this problem is I'm going section by section. Remember, there were 3 main sections to the mass spec. We had the accelerator, the velocity selector, and then the circular motion part. How I'm solving it by breaking it up into those 3 components mathematically, okay? So in the accelerator section, I solve for what velocity would the particle have as it enters into the velocity selector. We know that this is the velocity that they're going to enter into the second section with, okay? So, and that's the exact velocity that they would be undeflected, okay? So we know that that exact velocity that they were undeflected was equal to E over B. Now we want to solve for E, the electric field strength, because that was the question here in letter A. What magnitude and direction of electric field is needed? Okay, so we figured out that the electric field direction is going to be pointing up, and now we're solving for the magnitude, the electric field strength. So we just rearranged our equation, and we're going to plug in the velocity that we got from the accelerator section, and we're going to plug in the uniform magnetic field strength that they gave us in the problem, and we are going to get 2.2 times 10 to the 5th newtons per coulomb, or volts per meter. Remember, either of those are correct units for electric field strength. And then the direction was up. And then the very last section of this is going to help us answer part B of the problem, where they asked us to find the radius of this proton's circular motion path. Okay, so we're going to use our F-net statements. Okay, so the first F-net statement is, and this is circular motion, so it's F-net in the n-axis. Okay, and so we're saying that's mass times centripetal acceleration, which is mvt squared over r, and this v is velocity, so it should have a vector symbol over it. Okay, and then the second F-net statement is the sum of all the forces pointing inward, and in this case that would be only the magnetic force, because in part B it says the electric field is turned off. That means the only field that exists anymore is the magnetic field, so the magnetic force is the only force that is acting on that proton. So now we're going to set our two F-net equations equal to each other. So the magnetic force is equal to the centripetal force. So we have QVB equals mvt squared over r. We can cancel out one of the velocities. So we got QB equals mvt over r. And now we're going to solve for r. The easiest way to do that, since this r is in the denominator, is to flip both upside down, right? You've seen me do that before. So I'll just do it on this page here real quick. We've got QB, which is the same thing as QB over 1, and that's equal to m times VT over r. Whatever I do to one side of this equal sign, I got to do to the other. I need this r to be in the numerator, so I'm going to flip this fraction upside down, which means that I need to flip this fraction upside down. And now I'm solving for r, so that means I'll multiply both sides by m times vt, the tangential velocity. Okay, so the radius is equal to the mass of the proton times its tangential velocity divided by the charge of the proton times the magnetic field strength. So that's what we have right here. We've got values for all of that stuff, the mass, the velocity that we got from the section number 1, the accelerator, up here at the top. We have the elementary charge of the proton, and we have the uniform magnetic field strength that they gave us in the problem. So we type all that stuff in, and we get 0.0091 meters, or 9.1 times 10 to the negative 3rd meters is the radius. All right, cool. Well, that is a mass spec problem from start to finish then. And you would always break it up in those same 3 steps. You would have your accelerator section, and then you would do your velocity selector section, and then your circular motion section to answer any of those questions. All right, well, that's it for today. Bye.